This is Alex from Kenyon Academy. Today we're going to go over the Hammond postule and free radical halogenation. So off to the start, we're going to go over what the definition of the Hammond postule is. It says that species of a reaction that are close in energy are also close in structure. So we have to go over our energy diagram first here and some basic definitions. All energy diagrams go over the y-axis of energy, and it follows that energy throughout a time of a reaction. In this case, if you should remember from Gen Chem, if the product has more energy than the reactant, then you're storing energy, so it is an endergonic reaction, which for selectivity is really good, and endergonic reactions usually end up with a very selective product, in this case of halogenation. So what we're going to do in this case is go over the propagation 1 step. I shall go over the steps a little more in detail afterward of this selectivity explanation. But basically, in this step, we already made a radical and react it with this material we want to add that radical to. But before we can add it to that, we actually make a weak acid, or actually a weak or strong acid, depends, and we end up with a radical of that starting material, which later will actually help us get our product. But in this case, we can use the Hammond postule of this reaction to compare its reactants to its products to find what its transition state looks like. And the transition state in this case, or actually in all energy diagrams, are represented by this symbol, the double dagger. Now, and that is always put at the top of your energy hill, right above here. Anyhow, so using a Hammond postule, we can identify we have 3 species in this reaction. We have the reactants, the product, and the transition state. So our transition state is at a higher energy than the rest, but it is closer to the product than to the reactant, which is way over here. That means that it's going to be much closer to the products of this reaction, in this case HBr, because it's the stable product, than its unstable neighbor, the radical. So we can compare the transition state of the mechanism. In the mechanism, we can draw out, we always use half arrows when dealing with lone electrons. Remember, usually you use this double-sided arrow, but here you use half arrows. And let me isolate one of these H's to show the mechanism more clearly. So it takes that H, and that H leaves one of its electrons with the C. It takes one of its electrons and attacks the B as well to make a new bond, and it gives another electron back to the C that it was sharing originally. And that's what makes your compound. Now the transition state is this fighting off that mechanism. So what it looked like when they're tugging a war for that H is here, where the methane is fighting for the H with the bromine. Now these dots over here are usually shown to show the loser of the person that's losing the tug of war, while the dashes are shown to represent the person that's winning the tug of war. As we said, in this case, the transition state is very close to the product. HBr is our product, so this is winning the tug of war in the transition state. What that means is Br is more likely to pick a carbon that will have a stable radical intermediate. Radicals are our most stable, the same as carbocations, and be sure to watch our video on stability of carbocations and radicals along with carboanions, but just know that often it favors tertiary in this case. Now I can show that as well in the selectivity down below. Generally, iodine will be your most selective, then bromine, chloride, and fluoride. Fluoride being very unselective. In fact, it's so unselective that it will explode in most cases, so we don't really use it in lab. On the opposite side, iodine's so selective that it won't really react. That's because it's so endergonic, you need to actually give it a bunch of energy for it to react. You need to make the reaction work at about, I believe it's 500 Kelvin for it to go pretty decently. But even then, that's a lot of waste. We might as well just make a bromine. That's why these two are the most common reagents we use, because they work pretty well at room temperature. Bromine being really selective, and chlorine's a lot less selective, so it will work with all these different subs basically. This is what I mean by selective. It will pick a spot that is not very stable. So primary radicals will form, tertiary radicals, secondary radicals, and all other types. It doesn't matter. It doesn't care. It just wants, it's so unstable it wants to react with any of these. Bromine's more picky. It'll pick only the most stable spot, which for radicals is the tertiary in this molecule. So you'll end up with a huge mix of the chlorides because you'll get all the reactants. And the bromine you'll only end up with one because it's very selective. If you looked at the graph of chlorine to reactant, it would be much closer, the transition state would be much closer to the reactant side. That's because this here is an exothermic reaction, which is way more favorable. That's why it goes by faster. Exothermic is the thing we want, but endergonic lets us get more selective. So here, our transition state is much closer to our reactants, so it doesn't have to worry about being so unstable. So we draw the reactants winning, so the H is winning here, and the radical is losing the fight. So it gets the dots. On to our mechanism of free radical halogenation. It looks like a lot at first. Definitely takes some memorizing, drawing this out several times. Now remember, in the beginning, we often see UV light starting it, but you could also use heat. And what this does is it breaks the bond into radicals to start it off. That's why it's called initiation. So you get those two half arrows and you end up breaking that bond into two free radicals. That's important for our last step, which is in termination, because technically, since we have a bunch of different types of termination, you can really go from initiation straight to termination if you took this option here for one. If you hit both of those radicals back together again, those two half arrows go together to a bond, you can end this game really quick and not get a reaction. But of course that's no fun at all, so we're going to go over the propagation steps. Propagation steps basically keep the reaction going, because we really were using a bunch of chloride and a bunch of methane. We're going to make a lot of this because we're trying to get a bunch of products, because we're trying to get a whole synthesis going. So propagation 1, we use our new thing we just created, our radical, and we react it with what we want to put it on. But before we can actually put it on, we have to make the free radical version of our desired product. So what will happen first is what happens in phase 1 is you make your acid. That's a good way of memorizing it. So you get these two steps where the H and Cl come together to make hydrochloric acid, and the other arrow ends up to make your free radical that you want to put the product on. So you end up with your acid along with half of your desired product. Now to actually make your desired product, we need propagation 2. Now we have half of the product we want, and we're going to react it with another chloride. Now, we have to also worry about keeping this going. So what we actually end up doing is we make a new radical by only using one of the chlorides So one of these chlorides actually makes our product, as shown by these two arrows here coming together, and the other arrow goes off on its own to keep our reaction going. So now we have a new Cl and our product. So basically, propagation 1, we make an acid, often shown by HA, and we start making half of our product. Half of product. In propagation 2, we make our product and we also get propagation 1 going. Back again, that's why they're propagation 1 and 2, because they can just keep building off of each other. So now you can use this free radical and go back here. Now, with these very reactive radicals, you shall have these different spots of termination. As I said before, we can end this pretty quickly just by reacting those chlorides together. Please note that we generate a net 2 in the beginning of this, so we always have an option to terminate with one of those, or we can get 2 of these propagation cascades going. So we can technically react this with 2 methanes and get 2 reactions going. And if you do that, sorry for the ugly arrows, I'm not going to go any further down than that. Just know you're basically going through 1 and 2 with both of them. If you get that going, which you likely will because these are really unstable, you can also terminate with one of the intermediates from propagation 1, so half of your product. And you could also terminate with 2 of those intermediates, basically anything. In fact, it's really anything that you could even contaminate it so easily, or you can even, the radical even react with the wall of your test tube. Just so it's so unstable, it'll even try to take apart whatever that's made of to begin to end this reaction. Definitely draw this out a couple of times on your own and read about it all you can. This takes several steps. It's good to memorize the emphasis just to know where you're going. Definitely know that you're making an acid in propagation to know what you're doing, and you make half your product. Then propagation 2, you actually make that propagation. You actually make that product, and then you keep propagation 1 going. You keep the fuel to this reaction going. Why is this important? Because in synthesis problems, whenever you're given an alkane from now on, so anything without any functional groups besides alkane groups, from now on in the class you need to know the only thing you can do to this thing is give it either chloride or bromide and use UV light or heat to actually react this and use this for several other reactions you're going to learn later in class.